Okay, so I hope the screen is visible, right?
Yes, ma'am.
Okay. So, yeah, so thanks a lot for coming in the morning, for those of you who are here. So we were looking at constrained optimization problems yesterday. And specifically, we were looking at this form where you write the function as it has to be minimize f of x, and you have inequalities written in this form, gix less than or equal to 0, and a couple of equalities written in this way, jx equal to 0. Okay, so what we saw yesterday was we handled each of these cases separately. We took the case where you have only equalities, we took the case where you have only inequalities, and for each of these cases we wrote down some conditions that must get satisfied for an optimum. Okay, and then finally we brought all of them together, and so we had some condition like this where which involved the gradients of the function and the gradients of the constraints as well. And you had these multipliers for each of these gradients for the constraints. Okay, and in particular for the inequality constraints, we had this summation. So this grad fx plus the summation, for all the constraints. This only involves the active constraints. So at x, which is an optimum, which is guessed to be an optimum, you list down the set of active constraints. So just a reminder, the active constraints are the set of all constraints which get satisfied with equality. Okay, so something like this. These are the active constraints. So the set of all constraints at which gix is 0. Okay, so the optimality condition, if you remember, we had in the summation we only had the active constraints. So for the other constraints don't really matter at the optimum. Okay, and of course equality constraints by default they're always active, so those get included as well. Okay, and one thing to remember was these multipliers lambdas were greater than or equal to 0 for the ones corresponding to the inequalities, and when you looked at the multipliers corresponding to the equality constraints, the gradients of the equality constraints, those didn't have to be greater than or equal to 0, and those were unrestricted. Okay, so where we ended last class is trying to unify all of this, and instead of having separate conditions for equalities or inequalities, we're trying to write them as just one single set of conditions. Okay, so towards that, we defined the Lagrangian function. So the Lagrangian is a function of any point x and these multipliers, lambdas and mu's. Okay, and this is the functional form. So f of x plus summation lambda I gix plus summation mu j at jx. Okay, so yesterday when I wrote it as though, even the summation in this part, the inequality part, I wrote as though it is only for the active constraints. So yes, essentially it is going to be that way. It is going to, when you finally evaluate it, it's going to have only the active constraints. But the way in which the Lagrangian is written, you will write all the constraints. Okay, so one of the purposes of the Lagrangian is that you don't want the summation over active constraints. So you have to go and identify and write it. So you don't want that. So that's the reason why you write it as summation lambda I gix, where this is over all the constraints. Okay, so here let me just make it very specific. So these GIs, so this is for all I equals, let's say 1 to m, and this is for j equals 1 to l. Okay, so this summation here will be for I equal to 1 to m, irrespective of what is active and what is not active. Okay, and j is 1 to l. Okay, so you can define this for any point x. I mean, not only for the optimum, but the idea is to use it to characterize the optimum point. Okay, so then we listed out a set of constraints like this. So where the first one is gradient of this Lagrangian function with respect to x is 0. So what this will boil down to, so this gradient of the Lagrangian x lambda mu, so this being 0 will boil down to whatever the condition we wrote yesterday. So it's just with respect to it's with respect to x. So gradient of f of x plus now this one, so summation lambda I gradient gix, so I equals 1 to m, plus summation mu j and gradient of hj. Okay, so this is j equal 1 to l. So this is the gradient, and this has to be equal to 0. Now, in order to ensure that only the active constraints are included here, we have this condition, which is lambda I gix is 0 for all I. So whenever gix is less than 0, so the constraint is inactive, then the lambda I will be set to 0. Okay, so you can remember that we saw something like this in the context of duality, right? In dual LPs. So the idea is the same thing. Okay, so this condition is actually called complementary slackness. So same as what you saw in the case of the dual. Okay, so complementary slackness. So if one is slack, so if the constraint is slack, then lambda is 0. So that's what it means. Okay, and of course, based on our other conditions, we saw that lambda is all have to be greater than or equal to 0, and the point has to be feasible. So that's where you have gix less than or equal to 0 for all I equals 1 to m, and jx equals 0 for all j equals 1 to n. Okay, so these were the conditions we saw, and such a point which satisfies these which satisfies these set of equalities and inequalities, this pair of or the tuple of x, lambda, and mu, which satisfies these. This is called a Kkt point. Okay, so Kkt stands for Karish-Tucker. We'll just see in a minute like why it's called a Kkt point. Okay, so now before just say that this is going to be the optimal conditions, there's one more thing to keep track of, so which is called the regular point. Okay, so let me very brief what it is. So a point x, x bar, where the set of vectors, take all the active constraints x bar, and you take its gradients. So if all these gradients are linearly independent, such a point is called a regular point. Okay, it's a simple definition. Okay, so based on this definition, what you have is, if you take the interior point, the feasible set, so this omega is the set of all x, at gix less than 0, and jx to 0. Okay, so if this point, I'm going to take interior of this set, all of the regular points. Okay, so maybe let me just, so I think is not there. So consider you only have inequalities. So here, if for the interior points, none of them are going to be satisfied with equality, these constraints. So all of them are, for all of them, if set is null, I mean, there is empty. So by default, these are regular points. Okay. If you also
Ma'am,
equality, yes.
your audio is cutting out for some of the students.
Oh, is it? Let me just increase the mic volume. Better now?
Not really, it's quite choppy. I mean, you can hear a few words and then that's it.
Oh, okay. I don't know if there's a problem with my internet, but are you able to see the screen and the video is fine?
The screen is fine, but we cannot understand what you're saying.
Ma'am, maybe the bandwidth is limited. You can try switching off the video. It might help.
Yeah, I think I will do that. I will keep the video off. Is it better now?
Yes, ma'am.
It's better? Okay. Yeah. Okay. Fine. So just let me know in case it happens again. So did you hear this part, like where I defined
Ma'am,
a regular?
could you please start regular point again? The audio was a bit
Okay.
choppy.
Okay. So yeah, so let's just start from the regular point again. So a point x bar is when you say it's a regular point, then you take all the active constraints at x bar, and if the gradient of all these active constraints, those are linearly independent. Okay, so such a point is called a regular point. Okay, now consider the case where you only have inequality constraints. And then if you look at all the interior points of the set, okay, so then yeah, all the constraints are inactive at such an x, And so by default, the set of active constraints is empty. And so by default, you have that this is true, that everything in the active set is linearly independent because active set is anyway empty. So all the interior points are also regular points. Okay. So is this audible now? Is it better?
Yes, ma'am.
It's fine. Okay, cool. So now, additionally, if you have some equality constraints, okay, so now you remember that the set of active constraints, if you have equality constraints, it's, all these constraints, GIs, which are equal to 0. And additionally, you will also include all the edges. Okay, so now if you have these equality constraints, you say that x bar is a regular point if the gradient of gi and also gradient of hj. So gradient of gi for all these points such that gi x bar equals 0. Okay, so that is the set. And all other, for all the equality constraints, if you take the gradient, if this whole set of vectors is linearly independent, then you say that x bar is a regular point. Okay, so the reason why regular points become why they play a role is for this kind of an optimization problem that we have been seeing. The necessary condition, right, for x star to be local, to be a local optimum. So we saw some of these things, right, about a Kkt point. So only if x star is a regular point and if it's a local optimum will these conditions be satisfied. Okay, so remember in the case of unconstrained optimization, there was no notion of regular point. There were no constraints by default. Okay, so there if you had a local optimum, then it was just gradient of f equals 0. Now the difference is in constrained optimization, if x star is a local optimum, additionally if x star is a regular point, only then you can be sure that these conditions will be satisfied. Okay, so the Lagrangian plays a role. The gradient, instead of the gradient of f being 0, here you have the gradient of the Lagrangian being 0. Okay, so you remember, like in the case of interior points, right? So for interior points, you have that, the gradient f is 0. So all the lambdas, none of them play a role there. So that is also going to get satisfied in this condition. Okay, so if you look at this here, because of this complementary slackness, for all the interior points, gix is going to be less than 0. And so lambdas for those will be equal to 0. So now if you take this condition, so all these lambdas are 0. Okay, so a point, the case where you only have inequality. So all these are going to be 0. And these don't exist because there are no equality conditions. So the resulting condition, this gradient of the Lagrangian being equal to 0, is just going to give you gradient of f equals 0. Okay, so that's what we saw earlier when we talked of the inequality constraints. We want that to happen. Okay, so so this is a subtle point that you need to note, that this is a necessary condition only when x star is a regular point. Okay, and so we won't go into a proof of this because there are a lot of things that are needed to prove this, things like tangent surfaces, normal cones, and all that. So I think that would just take away the focus of and the objectives of the course. Okay, so so we'll not go into it. So this is the reason why I was telling you, like in all these textbooks, you would see many things starting from this point, that they define a regular point, or they give a motivation for why you need a regular point, and it can get a little messy with some technical details. So we will not go into the proof of that, but I'll later show you some examples of what breaks down when you don't have regularity. Okay, so I hope these conditions are clear. Okay, and this is actually called the first order Kkt conditions, and these are necessary conditions for x star to be optimal when x star is a regular point. Okay, are there any questions till this point?
Ma'am, in KKT conditions, we mentioned in the second condition that lambda I gix equal to 0, and the second last we say gix is also less than equal to 0. But since
Yes.
we are only considering the active constraints, why are we like extra, like writing it extra that GIX is less than equal to 0?
Okay, so in this form that we have, it's not only for the active constraints. We are writing it for all I equals in 1 to n. Okay, so this is not only for the active constraints. Okay, so in order to capture that in this gradient L, x lambda mu equals 0, in that equation, you only want the active constraints to show up. So for that reason, you're saying lambda I gx equal to 0 for every I. So this is also for all I, not only for the active constraints. Okay, and similarly in the definition of the Lagrangian, it's actually for the summation is over all i's. It's not only the active constraints. But true, because of this complementary slackness condition that comes, later on when you evaluate this, it turns out that you will only have the active constraints in the summation. For the inactive constraints, you will get lambda as 0 because of the complementary slackness. Okay, so the whole idea is like you don't want to, when you write a general condition, you don't want to, it makes it easier if you don't have something written for, like where you distinguish between the active and inactive constraints. Because, in terms of solving abilities and like for the solver and all that, it makes it a bit easier to write it in this way, a general formulation. And this one is exactly going to, capture this notion, this lambda I gx equals 0 is going to capture the notion of active constraints. Okay, so otherwise this is for all constraints you will write lambda I gx equal to 0 and gix less than or equal to 0. So this is just telling you that the point x is feasible for the original problem. So this is the original problem, right? So gx optimum point. So this is x star. Okay, so I make this like always. So this is all at x star. Okay, so x star has to be a feasible point. That's why these two conditions are there. Okay, so this is for feasibility. Okay, so Siddharth, is it clear?
Yes, ma'am. Now it's clear.
Okay.
Ma'am,
Yes.
we need to have all the optimal points to be they always have to be regular points, right?
They don't have to be regular always. So sometimes you might have a point which is optimum but which is not regular. Okay, so in that case, these conditions need not hold.
So it could be optimal, but it won't satisfy these Lagrangian conditions.
Yes, that can happen. Okay, so I'll give an example of that case. Okay, so yeah, are there any more questions, any concerns on this part?
No.
It's fine.
If a point is not a regular point, how do we check if it is optimal?
Yeah, so for that, there is really no condition that we can tell in this manner. Okay, so yeah, that is an issue. So that really cannot guarantee. So these work only for regular, it works only for regular points. And one other thing is you have something called sufficiency conditions. So these are only necessary conditions. Okay, so what this means is that if you're given that x is optimum, you know that these will be true. Okay, but there may be some other points which don't even satisfy these conditions. That can also happen. So it's like in your unconstrained optimization, we see that the gradient f equals 0, right? And that is a necessary condition. So if you want to filter out some points, if you want to say that some point is not an optimum, then you can use this. Okay, you can narrow down your search to these points, which will satisfy the Kkt conditions. Okay, so that's the idea of these. Now, at sometimes these conditions, under some cases, these first order Kkt conditions will also be sufficient. So that means in that there are some classes of problems. So it's actually convex optimization problems where if you find a Kkt point, then you can be sure that that is an optimum. Okay, so we will see why that's the case later. But in all generality, for a general nonlinear programming problem or a general constrained optimization problem, these are only necessary conditions. Okay.
Yes, ma'am.
Cool. So now let us just see an example of how we can apply these KKT conditions. So I'm taking this problem. So minimize x1 plus x2. I'm just taking in smaller dimensions so that it becomes easier to, you can verify your solutions also. Okay, but you can also do the same things for, larger dimensions problem. But for example, we'll take, in 2 dimensions. So the problem is this: minimize x1 plus x2 such that x1 square plus x2 square is less than or equal to 2 and x2 is greater than or equal to 0. So it's so just to write it in the form where gx is less than or equal to 0, I've written it in this manner. So this is actually g1x. So g1x is actually x1 square plus x2 square minus 2 is less than or equal to 0. So g1x is this function, x1 square plus x2 square minus 2. And g2x is this function, minus x2. Okay, so now, and this is the function f of x. Okay, so let us write the Lagrangian here. So the multipliers, I'll call it lambda 1 and lambda 2. Here there are inequalities alone. So let's just write the Lagrangian. So the Lagrangian is a function of x, lambda 1 and lambda 2. Okay, so this is just f of x plus summation lambda I gix. Okay, in this case. So can you tell me what that is?
x1 plus x2 plus
Yes.
lambda 1 x1 square plus x2 square minus 2
Yes.
plus minus lambda 2 x2.
Minus lambda 2 x2. So this is the Lagrangian. And the first condition says that gradient of the Lagrangian with respect to x is 0. Okay. So let's take the gradient now. Can somebody tell me?
The first, with respect to x1, it will be 1 plus lambda 1 x1.
So
2
2
lambda
lambda.
1, 2 lambda 1
Yes.
x1.
Yes.
And for the x2, it is 1 plus 2 lambda 2 lambda 1 x2 minus lambda 2.
2 lambda 1 x2 minus lambda 2. So this is equal to 0. So both these conditions have to be satisfied. Okay, and yeah, so this is one of the conditions. So now in order to find a point which satisfies this, we will look at it case by case. In the sense, first case is, let's take that both constraints are active. So both G1 and G2 are active. Okay, so what that means is it's x1 square plus x2 square equal to 2. Equal to 2. So x1 square plus x2 square minus 2 is 0. And also you have minus x2 is 0. So x2 is 0. Okay, so this is what it means to say that both are active. Okay, so now if you see x2 is 0, so what you have is x1 square is 2. So x1 is plus or minus root 2. Okay, so the points the x's which satisfy these active, when the case where both constraints are active, so the set of points is root 2 0 and the other point is minus root 2 0. So these are the two candidates here. Now let's see what happens when you substitute the value here. Let's try to find a lambda 1 and lambda 2. So here you also should have lambda 1 greater than or equal to 0, lambda 2 greater than or equal to 0. Okay, so when you substitute this, what do you get? So x2 is 0. So what can you say about lambda 2?
1.
So lambda 2 is 1. So let's take first the point root 2 0. So this is x. Okay, so lambda 2 is 1. Now what is x1? Lambda 1.
Minus 1 by 2 square root 2.
Yes, minus 1 by 2 square root 2. So I'm substituting this value here in the equation from 1 plus 2 lambda 1 x1 is 0. Okay, so these are the two values you got. Now you see that you wanted lambda 1 to be greater than or equal to 0, but this doesn't satisfy this. Okay, so lambda 1 here you got a negative value. So this is not a Kkt point. okay, not a Kkt point. So let's take the other case. Now we take x as minus root 2, 0. So again,
Lambda 2 is
from
1.
lambda 2 is 1. And what is lambda 1?
1 by 2 root 2.
1 by 2 root 2. Okay. So now this is satisfying all these conditions, right? All these conditions above. Okay, because anyway, these two constraints were active. And so complementary slackness is anyway satisfied. Okay, and then you have these lambdas are greater than or equal to 0. And this x is anyway feasible. Okay, so this is a Kkt point. Okay, so this is one Kkt point. Now let's just see, this is a case where both these constraints were active. So you have to take all combinations and see what happens. Okay, so let's take the case where now both are inactive. Okay, so what this means is x1 square plus x2 square is minus 2 is strictly less than 0, and minus x2 is also strictly less than 0. Okay, so because of complementary slackness, since both are less than 0, you must have lambda 1 is 0. So lambda 1 is the multiplier corresponding to the first constraint. So lambda 1 has to be 0, and also lambda 2 has to be 0. Okay, so remember that these won't show up when you take the gradient of the Lagrangian. Okay, so now can you tell me what these x's would be? Like, can we see what these conditions boil down to now? So lambda 1 and lambda 2 are both 0.
Not possible.
It is not possible, right? So from this condition, this is not going to be satisfied. Okay, so this would give you, like on the left hand side, you're going to get 1, 1. Right, and this will be the left hand side, and the right hand side is 0. So this cannot be equal to 0, right? So this is not equal to 0, so this cannot happen. Okay, so you cannot find a Kkt point when both are inactive. Okay, so now let's take the case where one is active and one is inactive. So let's take the case where G1 is inactive and G2 is active. Okay, so what this means is x1 square plus x2 square minus 2 is less than 0, and x2 is equal to 0. Okay, so because this is G1 is inactive, what you will have is lambda 1 is 0. Okay, lambda 2 you still don't know. Okay, so now can you tell me what these
Also not possible. 1 z.
So what do you get? So what were the conditions? 1 plus 2 lambda 1 x1 is 0, and the other one was what? 1 plus 2 lambda 1 x2 minus lambda 2. 1 plus 2 lambda 1 x2 minus lambda 2, right?
This one. So
Okay.
not possible.
Yeah, so this is not possible because this one will get violated. Okay, and what about this one? Yeah, this can happen by setting lambda 2 as 1. So anyway, so this is also not possible. So no Kkt point here. Okay. Now, the last case. So suppose G1 is active and G2 is inactive. Okay, so that means x2 is minus x2 is less than 0, and x1 square plus x2 square equal to 2. Okay, so this would mean lambda 2 is equal to 0. Okay, so what do you get here? So if you substitute these equations, so lambda 2 is 0, so you'll get 2 lambda 1 x2 plus 1 is 0. Okay, and you get lambda 1 plus 2 lambda 1 x1 is equal to 0. So can we simplify this further? So okay, so from here let's just see what happens. So it must be that x1 and x2 are the same, right? So x2 is -1 by 2 lambda 1, and x1 is also -1 by 2 lambda 1. So both these are the same values. So x1, it must be that x1 is equal to x2, right? So now when you substitute,
In this case, lambda 1 has to be greater than or equal to 0, right?
yes.
So, and since x2 is also greater than 0, is this also not possible? Isn't this also not possible?
Say that again. So lambda 1 is greater than or equal to 0, right?
And x2 is also greater than 0, the G2 inactive case.
Yes.
So, since x2 is -1 by 2 lambda 1, so this is also not possible, right?
Yeah. Yeah, actually, that's what it's going to happen finally. So, yeah, that's one way to see this. So, yeah, this is actually not going to be possible. That logic is right. So, another way to see it is you could actually solve it and then show that there is a contradiction here. But yeah, so maybe that's a simpler logic to go with. So, let's just say that, yeah, because lambda 1 is greater than 0 and you also have x2 greater than 0. And so this is going to get violated. Okay, this will be violated. So again, this is also not possible. So no Kkt point here. So now we have covered all the cases, right? So two cases where one active, one inactive, both inactive and both active. So this was the only Kkt point. And turns out that that is indeed a minimum point. So this is -√2 0. So if you see if you plot this and see, so the problem was again minimize x1 plus x2 such that x1 square plus x2 square is less than equal to 2 and x2 is greater than or equal to 0. So this was the problem. Okay, so in terms of the feasible region, what you're going to have is x1, x2. So the circle, okay, so that is, so this part is the feasible, sorry, not the whole of it. So this is the inner part of the circle is this constraint, okay, and so this is -√2 and here you have √2. And in particular, you want x2 is greater than or equal to 0. So the feasible region is just this. Okay, and the contours of the function, that's going to be something like this. This is x1 plus x2 is 0, and at this point you're going to have x1 plus x2 is -√2. Okay, so the function is always decreasing in this direction, and the best it can go is at this point. And this is actually a minimum, and that turns out to be a Kkt point. So one thing to verify is this point -√2 0. It's also a regular point. Okay, so both the constraints are active. So let's just see the gradient at this point. So gradient of g1 of x was what at -√2 0. What was the gradient? So this was 2x1, 2x2, right?
Yes.
So this is -2√2 and 0. And for gradient G2, so G2 was -x2 less than 2. So what you got as a gradient would have been 0 and 1, 0 and -1. Okay, so these two are linearly independent anyway. Okay, so that's why the Kkt point was at, I mean, you got this as a Kkt point. I mean, X was part of a Kkt point. Okay, so yeah, I hope this example has made things a little more clear. So are
Yes,
there any
ma'am.
questions? Yeah, good. So are there any questions? Anybody wanted to clarify anything? All clear? You can type.
So based on this, can we conclude that -√2, 0 is a local optima?
Yeah, so yeah, in this case, yes, -√2 0, -√2 0 is a local optima. So one thing is, this is a convex optimization problem. Okay, then it becomes also a sufficient condition. The moment you find a Kkt point, you can say that that is an optimum. Okay, but in general, yeah, you cannot conclude. You can just verify if it's, it's gonna, if it could be an optimum or not.
Yes,
Ma'am,
Yes.
So checking for regularity was necessary in this case to verify whether it was an optimum.
So in this case, like checking for regularity, yeah, it is only needed to ensure that you will have a KKT point. Okay, so I just wanted to illustrate what it means to check for regularity here. Okay, so here this is an example of a case where the optimum point is a regular point. Okay, and so it also satisfies the KKT conditions. I mean, if you ignore the convexity aspect, but this is a case where it is regular, and so you have, I mean, the optimum is going to be a KKT point. It's going to be part of a KKT tuple.
Ma'am, but
Okay.
in general cases, if we find that a point is KKT, do we then also need to go and check for regularity?
So usually, what happens is if you know, uh, the reasoning goes like this. Okay, so if you have a regular point, then you will get a KKT point. But if you anyway get a KKT point, usually there is yeah. I mean, you don't need to really ensure regularity. Okay. So that's the way it works. I mean, if it is not regular, then it's not even necessary that you will have a KKT point. Okay, so that.
Can you repeat the last statement if it's not regular?
So if the point is not regular, okay, if the optimum point is not regular, then there is no guarantee that you will find a KKT point. I mean, there's no guarantee that you'll find a KKT point with that optimum. So the KKT point has x lambda mu, right? So there's no guarantee that you will find a KKT point with that x. Okay, if it's not regular.
Oh, so for a problem where the optimum is not regular, we might not find a KKT point, but still like optimal.
Yeah, that there could be an optimum point, but this KKT point will not exist. Okay, so
All our
one thing,
KKT conditions will fail, but there will be an optimum.
yes.
Okay.
So I will just show you an example. So that's precisely the next point I was going to make. So what goes wrong when regularity doesn't hold. Okay, so we'll just see this with this example here. So I'm taking this problem again in 2 dimensions. So maximize x such that x2 is less than or equal to 1 minus x1 and x2 is greater than or equal to 0. So let me just plot this region. So so this is x1 and this is x2. Okay, so the first constraint here is, let me just plot 1 minus x1 cube. Okay, so 1 minus x1 cube, and I'll just plot the curve 1 minus x1 cube equal to 0. So that would be like the curve, let me just say 1 minus x1 cube equal to 0. I'm just going to plot that. So when x1 equals 1, the value of x2, I mean, this one is, so yeah, sorry, it's not 0, but rather x2 equal to 1 minus x1 cube. Okay, let me just plot this one. So when x1 is 1, x2 is 0. So you get this point. Now, when what else happens? Now, when x1 is 0, what you're going to get is x2 is 1. Okay, and for points in between, so something like x1 is half, you're going to get something like 1/8. So maybe something here. Okay, so the curve is going to look something of this form. Okay, it's a nonlinear curve. Okay, so something like this. Okay, so this is the curve 1 minus x1 cube is equal to x2. Now the constraint here is x2 is less than or equal to 1 minus x1 cube. So to see which side it is, you can see one of the points. So 0, 0 will satisfy this constraint, right? So x2 is 0 and that is going to be less than 1. So the feasible region is corresponding to this side. Okay. And you also have x2 is greater than or equal to 0. So the feasible region is everything in this part. Okay, so till here. Okay, so now you see from here that the point where the objective is maximized is where x1 is maximized. So it's only exactly this point. So this is the point 1, 0. Okay. So now let's see what happens here. So I will just write it in the form that we require. It's in max and, it's not in the form that we assumed. So this will be equivalent to, so this problem is equivalent to minus min minus x1 such that x2 minus 1 minus x1 q is less than or equal to 0 and minus x2 is less than or equal to 0. Okay, so this is G1 and this is G2. Okay, so now let's just see the gradient of G1. So what is gradient of G1 of x in general?
Three 1 minus x1 square.
3 1 minus x1 square. Yes.
Minus
And
minus it
so
cancels
1,
out.
right? G1 is x2 minus this, so it's just 1 here.
That's right.
Okay, and gradient of G2 is what?
0 and minus 1.
0 minus 1. Okay, so now, and also, yeah, what is gradient of f also, can you tell me? So f is now
Minus
this
1,
1,
0.
okay? So minus 1, 0. Okay, so in particular at the point 1, 0, so at 1, 0, gradient of G1 is what?
0. 0, 1.
0, 1, and gradient of G2 is anyway 0 minus 1. And gradient of f is minus 1, 0. Okay, so in terms of, if I try to plot this on the figure, so the gradient of G1 is 0, 1. So it is pointing in this direction. So this is gradient of G1. Now gradient of G2 is 0 minus 1. So it is in this direction. Okay, now the gradient of f of x is minus 1, 0. So that is something like this. Okay, so this is gradient of f of x. Okay, so now remember what this Lagrangian condition is telling you. So the condition that we have was gradient of f of x plus lambda 1 gradient of g1 of x plus lambda 2 gradient of g2x is 0. So this is the case because both these constraints are active. So at this point, x2 is equal to 1 minus x1 cube and x2 is also equal to 0. So that's why the Kkt condition actually boiled down to this. Okay, but can this be satisfied? So that's the thing that goes wrong here. So if delta fx is minus 1, 0, and you want this to be expressed as minus lambda 1 times 0, 1 plus minus lambda 2 times 0 minus 1. Okay, so you see that you're trying to combine two zeros here to get a minus 1. Okay, so that is the issue that's happened. So you cannot get gradient fx using a combination of these two directions. So these are actually giving something in the same direction. I mean, of course, they're parallel and they point in the opposite directions. But this other orthogonal direction is something which is not taken care of in these gradients of the active constraints. And so that's where it fails. So that's why this gradient of f of x, it's not able to form that using these two. Okay, so that this is an example where the optimum we know is 1, 0, but it's not a regular point. So you see that these two are 0, 1 and 0 minus 1. So they're actually linearly dependent. So gradient G1 and gradient G2 are linearly dependent. Okay, so this is not a regular point. Okay, so I hope this example has is clear, like what what I'm trying to illustrate here. Are there any questions on this example?
No.
Okay. Okay, so these are some cases where the regularity assumption is actually needed here. Okay, so yeah. So now one thing here is the problem convex here? It's not convex anyway. Okay, so it's out of question. So yeah, so now another example I have to illustrate the same thing about about the regularity assumption. When it is violated, you may not find a Kkt point. So that's this example. So I will leave it for you to try it out as an exercise. Okay, so the problem is this. The objective is again linear, but the constraints are like this: x1 minus 1 square plus x2 square is 1, x1 plus 1 square plus x2 square is 1. Okay, so so this is of the form of all equalities. Okay, so geometrically this figure is like this. So this is the curve where x1 minus 1 square plus x2 square is 1. So this length is 1. Okay, and this is the other curve. Okay, so it's an equality constraint, so all points on the curve, nothing inside. Okay, so a point which satisfies both these simultaneously is there is only one point. Okay, the feasible point is only one point here, which is 0, 0. And this is the only feasible point and it is the optimum. But you will see that, regularity fails here. So you cannot satisfy the Kkt conditions. Okay, so I will leave it for you to try this out. And one thing here is, the Lagrangian multipliers. Okay, so these quantities that we multiply with each of the constraints, those are called Lagrange multipliers. Okay, so those ones in this case they are unrestricted in sign. Okay, so for if you had inequalities, they were greater than or equal to 0. But here the mu1 and mu2 that you're going to multiply these with, those are unrestricted. So that's something you have to keep in mind. So just try this out and see what happens and see where it fails. Okay. So this is homework. Okay, so now another point I want to make is, I've been telling you that its Kkt conditions are necessary, but they're not sufficient for local minimum. Okay, so to see this, you can have, this is one example, this is in one dimension. So the point, I mean, in terms of the, the geometric region, so this is x, and so this here I'm plotting f of x. Okay, so the function is minus x square, so it looks like something like this. Okay, so x square would have been a parabola of this form. And so this is minus x square. Okay, and you're looking at this region. So the feasible region is x less than or equal to 0. So this part. Okay, so this is the feasible part. And yeah, so you can see that it's an unbounded function. The objective is going to negative infinity. Okay, so minimum doesn't exist here. But let's just try to see what the Kkt conditions give you here. Okay, so first thing is, the points which are regular. So just check regularity once. Okay, so in terms of, so this is f of x and this is g of x. Okay, so the gradient of g of x is just 1. Okay, and this is not equal to 0. So it is a regular point. So if there is only one vector, as long as you don't get the 0 vector, it is going to be linearly independent. It's a linearly independent set anyway. So this, any point you take here in this feasible region is a regular point. Okay, so the optimum is also a regular point. Okay, but let's just see what happens with the Kkt conditions. So tell me the Lagrangians. So there are two, x and lambda. So what's it going to be?
Minus x squared plus x, lambda x.
Plus lambda x, right? So now the gradient, it's in one dimension, so you can just write d by dx is 0. So
Minus
what is
2x
this
plus
given?
lambda.
Minus 2x plus lambda is 0. So lambda is equal to 2x. Okay. So, yeah. So so lambda, so at the point x equals 0, so at x equals 0, what you're going to get is okay, so I think we shouldn't do it in this way. Let's just try to do it in the way we did earlier. So suppose x is less than 0. Okay, so constraint is inactive. So if the constraint is inactive, then x is less than 0, so lambda is equal to 0. Okay, and so this would mean that 2x equal to 0, and this gives you x equal to 0. So this is anyway not possible. So this is not a Kkt point. Now let's take the case where the constraint is active. So that means x is equal to 0, which we know now that this is the optimum. But anyway, x is 0, so lambda is equal to 2x, and that is 0. Okay, so it satisfies that you want also that lambda to be greater than or equal to 0, so that is satisfied. Okay, so this is a Kkt point. Okay, so this is a Kkt point. But you see here that this is actually a maximizer of this function. So this is x is, I mean, part of this Kkt point is x is 0. And this is actually a maximum rather than the minimum. Okay, so these kind of issues can happen. So they're necessary, but they're not always sufficient. Okay, so this is something to keep in mind. So I have another example. So this is another example to illustrate this point. So here you have, I mean, this is the example that we had been talking of, to motivate the whole set of optimality conditions. So this is x1 square plus x2 square equals 1. So everything on the circle, and the function is linear. So it's x1 plus x2. And here we know that this is the minimum point and this is the maximum point. Okay, just by the geometry of it. So try to compute the Kkt points here. This also, I will leave this as an exercise. Okay, so try this and see what happens. So what I will just tell you the result beforehand so that you can verify that. So both these points you will get it as part of a Kkt point. So there will be 2 Kkt points you will get, one corresponding to the min and max, and one corresponding to the max. Okay, so at both these you have a Kkt point. So that's kind of illustrates the idea that these conditions that we saw here are necessary but not sufficient. Okay, so now there are actually something called the second order Kkt conditions. So like in unconstrained optimization, you saw the first order condition, which was that the gradient is 0. And you had second order conditions which looked at the Hessian of the function. And you had things like the Hessian has to be positive semi-definite or positive definite and so on. Okay, so such similar conditions exist even for constrained optimization. So you have some second order necessary conditions, and you also have a second order sufficient condition. So that all those will make use of the second order, the Hessian of the Lagrangian. Okay, so the equivalent function here you see is a Lagrangian instead of gradient of f. So here we will look at the Hessian of the Lagrangian, and the sum fixed. So you cannot say it's positive semi-definite. So because you want to account for the descent directions which are also feasible. Okay, so there's it's positive semi-definite along some cone. Okay, so we will not get into the second order conditions at the moment for lack of time, but you should know that these also exist. So at some point, if you're dealing with problems where you're unsure of whether this is giving you an optimum or not, that is something that you could try. Okay, now the thing is that the additional use of these first order Kkt conditions is in convex optimization problems. So in which case these conditions also become sufficient. So if you find a Kkt point, then you are guaranteed that it's an optimum. Okay, and many problems in machine learning and in several domains you can formulate them as convex problems, and that's where it finds the most use. Okay, so let me just go over this result. So in general, we saw earlier that for convex optimization problems, they're of this form, where the function f of x is convex and gix less than 0 and hjx equal to 0. So these are also convex functions. So g is a convex function. And in particular for the equality constraints, unless they are affine or linear, you will not get convexity. This region will not be a convex region. So the only way that this becomes a convex optimization problem is when hjx is equal to 0 and hj's are all affine. Okay, so this is something you might have seen in the assignment, right? When you were asked to find the values of some parameter of some function which makes it convex. Okay, it's an affine function, and if it is convex, it has to be that. I mean, if it's an equality and it has to be convex, then the only way is it's affine. Okay. Now, like we saw regularity in the case of general problems, for convex optimization problems, for the necessary conditions alone, there is an alternate requirement. Okay, so which is called a Slater point. Okay, so in regularity, that was a general set of conditions that you saw where the gradients of the active constraints are linearly independent. Now, this is an alternate condition which is called Slater's condition or Slater's constraint qualification. So all these regularity, Slater's condition, these are all called constraint qualifications because there are some additional things that you wanted to be satisfied. Okay, so what this condition is telling you is there is a point in the interior. Okay, so there is a point x0 such that gi of x0 is less than 0 for every constraint, for every inequality constraint, and x0 is a feasible point. So all these are also, the equalities are also satisfied. So such a point is called a Slater point. And in terms of the necessary conditions, so you remember that, we just saw that if x star is a regular point and its optimum, then it satisfies the necessary conditions. Okay, so now for convex optimization problems, instead of regularity, the necessary condition would be that, if x star is an optimum and if it satisfies Slater's constraints, then the Kkt conditions will be satisfied. Okay, so that's in terms of the necessary conditions. Okay, so you can check this with this example here. Okay, so one thing is, this, so this is a convex optimization problem. So the objective is linear and, this is kind of the inner region of a circle. Okay, so so you can just verify that here again 0, 0 is the only feasible point. So it boils down to the same set as I showed you for your homework exercise. So where you have one circle like this and another one like this, and it's all the interior regions of both. Okay, so the intersection of the interiors of both, and it's just this point. Okay, so the interiors of both means you have a convex. These functions are themselves convex. And the inner, the intersection is just this point, and that's the optimum. But so it is not an interior point, right? So at this point, like both the constraints are active. Okay, and so there is no slate. This kind of a point is also referred to as a Slater point. Okay, so there is no Slater point here. So even though this point 0, 0 is an optimum, it's the only feasible point, it's an optimum, but it doesn't satisfy this regularity condition, and it's also not going to satisfy this Slater condition. So you will see that it doesn't satisfy the Kkt conditions. Okay, so here's an example where, if you just try to apply the Kkt conditions, you won't get any solution here. Okay, even though the problem is convex. Now, what I told you was that for convex optimization problems, the Kkt conditions are also sufficient. Okay, so what it means is that, if you have, forget about Slater's point or regularity, somehow you apply the Kkt conditions and you got a Kkt point, then you can be sure that it's an optimum. Okay, but whether a Kkt point will exist or not, that will happen when you have these conditions. So either Slater's condition or these regular point is there, then you will be, it's about the existence of a Kkt point. Okay, so is this idea clear, like what I'm trying to clarify on this?
Yes, ma'am.
Yeah. Okay, so maybe I'm just running out of time, so I will tell you the proof of this in probably the next class. Okay, so yeah, I think I will stop here for now, and if there are any questions, I can take it.
Ma'am, can you recap the part with the Slater's point once again? I didn't get it.
Yeah, so so there are these conditions which are necessary, and there are some conditions which are sufficient. Okay, so these two things are, we distinguish between the two, right? For constraint problems also. For unconstrained also we saw that. Now for like, let's just talk of necessary conditions. Okay, so if x star is optimum, when can you say that there is a Kkt point? Okay, when will it be part of a Kkt tuple? So one condition we saw was, in general, if the active constraints are linearly independent, okay, then you are going to have that if x star is optimum, you will have a Kkt point. It will be part of a Kkt point. Okay. Now, in the case of convex optimization problems, yes, this regularity, that is also something which applies. So if you can verify that, the there is a point at which which is a regular point, and if it is an optimum, then it will satisfy the Kkt conditions. Okay, there will be a Kkt point with that x. Okay, that is anyway there. Now, an alternate condition instead of regularity, you can also check for what is called the Slater's condition. So what it's telling you is that, for such a problem, if there is a point which is in the interior for all these constraints, okay, so suppose this is the convex region, and so here there is an interior point, right? So maybe let me just write it. This is maybe too simple a constraint. So something like this. Okay, there are 3 constraints here, and this is the inner region. Okay, so some point here, and it's strictly in the interior as far as all these constraints are concerned. Okay, so that's called an interior point, right? So if you have such a point like this, which is truly in the interior as far as all the inequalities are concerned, and of course, in terms of equalities, there's no other go. You have to satisfy the equalities. So such a point is called a Slater point. Okay, so now instead of checking for regularity, sometimes it may be, for whatever reason, it may not be very easy to check for regularity. This is giving you another condition. So if the feasible region is such that there is a Slater point, okay, there's an easier one to check, right? Like you just see if there's an interior point. So if there's an interior point, then it is guaranteed that the optimum to this convex problem will satisfy the Kkt conditions. Okay, so there's going to be there's going to be a Kkt point containing the optimum in its tuple. Okay, so that's what these Slater's conditions are telling you. Okay, so so when Slater's condition doesn't hold, so if you cannot find an interior point, then again the optimum need not satisfy a Kkt point. At the optimum, you may not have a Kkt point, and such an example is this this problem here, where there are these 2 regions here, and at the intersection there's just a single point. Okay, and so there's no point which is strictly interior as far as both these are concerned, right? In this feasible region. So then here, what's going to happen is the Kkt conditions will not be satisfied. You will not be able to find a Kkt point here. Okay, though this is an optimum and it's a convex problem, but the Kkt point need not exist. So a condition where the Kkt point will exist is the Slater's condition. This is only for convex functions. Okay, Siddharth?
Yes, ma'am. Yeah.
It's clear? Yeah. So I'm not getting into the proof of this. Like there is a proof if you've seen Boyd about why this is true and all that, but I think it just goes into a lot of details. Like in the case of regularity, same kind of the issues happen here. Okay. So, in this similar manner, there are many other constraint qualifications also. Like sometimes it may not be very easy to check for regularity. So there are a set of alternate conditions also in the literature, but anyway, we won't go into all those details. So remember the Slater's condition in particular, because that gets used in many places, because these convex problems, they show up often, right? Okay, so in this line, the other part is about sufficiency. So suppose the problem is convex and you didn't check for Slater's condition, but you just tried to find a Kkt point and you actually found a point. Okay, irrespective of Slater's constraint, you found a Kkt point, then you can be guaranteed that that is an optimum. So that's what the next part is going to be, and we'll probably cover this in the next class. Okay. So is that clear, Siddharth?
Yes, ma'am.
Okay.
Thank you, ma'am.
Thanks. Tushar?